I wanted to show you something I've recently acquired. This is an HP oscilloscope, a 54645D digital oscilloscope. And I wanted to make this video because I felt like there weren't enough videos on YouTube that really show the capabilities of this scope and how well it compares to its analog counterparts. The first thing I wanted to show is just how responsive it is. It's extremely responsive to change. It doesn't feel slow like my old LaCroix did. It's very quick to respond to input. There is no discernible delay in most modes at all. This is with a microphone connected, and now I'll just do a function generator to show you how that looks. The controls are really easy to use. It's quite intuitive. Nothing is hidden very far in terms of menus. You've got controls for each channel that are dedicated, that are always here. Very, obvious controls for the most part. Let's look up a function generator. There we go. So that's at about, 748 hertz is what the generator reads. You can zoom in. You can see it respond immediately if I touch the function generator. That bounciness you see is actually part of the generator, changing frequencies. Responds right away. We can measure that frequency, the time, frequency, and there it is, 1.4439, and that's what the generator reads as well. I can show you the delayed sweep here. I press this button, it says delayed. I press delayed right here. Then I can zoom like this. So I can look at a zoomed in version and a zoomed out version at the same time. That's a pretty cool feature. And I actually find this easier to use than a similar feature that my Tektronix scope has. This actually can do that, but it's much harder to do. And this is pretty easy. We can also go into XY mode here, which isn't that exciting. It's just a microphone and a function generator. All right, enough of that. I'll go back to regular display here. Of course, one of the advantages of a digital scope is you can measure stuff. We can go measure the voltage peak to peak, or the RMS if we want that. All I did to measure is I just pressed the measurement button. It's pretty simple in this regard. So I like that a lot. Your usual math functions are here if you want to add the channels together or divide them or something like that. Triggering is right here. Just press edge and you can select the triggering source, and if it's positive or negative edge. It also has interesting triggering options to try to find glitches or to trigger on a standard NTSC video, which is not that useful these days for most people. Probably edge is what you usually want here. You can change the time reference so that you're starting in the center, left or right. You see that changing at the edge there. Center is kind of the standard option for most people, but left edge makes sense sometimes. One of the options I got on this scope, which I thought was really cool, is the FFT module for the back. It goes right here. And that FFT module lets you have a serial port, a parallel port for printing, and the ability to do a Fourier transform display on here. When you print it, it looks like this. And it probably prints faster than your Windows desktop PC. Let me show you how to use the Fourier transform real quick. So for the Fourier transform, and it's not an FFT, it's kind of slow, but let me show you how fast it goes. The first thing we need to do is show many periods of the waveform we're interested in. If you zoom in like this, which people would typically do, the Fourier transform algorithm only has, one period to work with, and you're not going to see very much. So you have to zoom out pretty far if you want to see a nice Fourier transform. So I'll do this. Go to the math menu, go to function 2, turn it on, go to menu, and you can choose the function you want. I've chosen FFT here. I'm going to go to the FFT menu, auto scale it, and then I'm going to turn off the display of the time domain. So now we're only looking at the frequency domain on here. And you can see the generator is pretty cool, pretty clean, I mean. We can measure exactly what that peak is if we go to cursors. But instead of, moving the cursor around like this, which we could do, we're just going to press Find Peaks. It's a really nice feature here. And it tells us that one peak is at 1.44 kilohertz and one is at 273 hertz down here. I don't know what that one is, but this one certainly is a generator. And you can see how fast it's refreshing right now. A couple times a second, right? If I move the frequency knob on the generator like that, you saw how long it takes. So looking at something like voice in real time is not too exciting, but it's certainly useful for looking at distortion artifacts. We can see where the harmonics would lie. One thing kind of finicky about this is you have to make sure you set this span correctly. You can go here and you can intentionally zoom in on the FFT, but when you zoom in like this, you're just losing display resolution. You can see it looking kind of chunky down here. So we don't want to do that. If you need to look at something up close, you want to change your time domain. So we're sampling, even more data or less data. So right now my span is 24 kilohertz wide. It's basically the whole audio spectrum. And we can see exactly where that is. I can pop this up to a higher frequency or a lower frequency. And if we want to zoom in, we can do like that. Let's see. There we go. It's not too bad, really. If you want to see how it looks on a microphone, let's do that. Previous menu. So we'll change the operand, that's the input, to A2. That's the microphone here. Hello, test 1, 2, 3, testing 1, 2. Audio. So you can see how fast it updates. It's not super fast, but it's fast enough to be useful still. Now, one thing I was hoping to be able to do with a display like this is make a Bode plot, a frequency response chart for a circuit. And that's a bit tricky to do on here. If you go to the display menu, there's a mode called peak detect, but it doesn't let you do it on the Fourier transform display. So that's no good. Your best bet if you want to try something like this is to go to the average menu, crank the averages up to something like 256 samples, and then continuously sweep the input or provide noise or something like that. And eventually you'll kind of get an idea of the frequency response of the signal. And in my case, I need to move the auto scale a bit up. You can also just change the reference. And as I'm talking, you'll see, this is kind of where my voice is, and you can see the K right here, not the K, the cutoff, because I don't have a whole lot of content up here in this range. Hello, audio. So that's really the best we can do to show the frequency response of something. Go back to normal mode here. That's what that does. Now, in addition to Fourier transform, you can also do some other interesting functions. Let me turn off a microphone here. Go back to the function generator. And let's display the audio A1. There we go. If I go into the math menu and select derivative. Now the derivative of this is going to show you the slope. The slope on a sine wave, if you recall, is the maximum around here and the minimum at the crest and the trough. And so if I change the scaling here, you can see if you remember calculus, a cosine turns into a sine turns into a cosine, plus or minus. And there it is. It's 90 degrees out of phase with the input, and that's because it's showing you the slope of this line, or the derivative. For example, maximum derivative right here happens right there on the side of the sine wave. And the minimum derivative, where this hits 0, is right there, the trough, or at the crest. See that? So, calculus, right? We can also do an integral operation. If we hit this button again, it's going to show us the integral. Again, you got to play with the scale a little bit to see it. There it is. Okay. So now we've integrated. And again, you can see it's really just a phase shift for this kind of signal. The integral is the area under the curve. And so we can see that we begin negative. So we've got more and more negative area. And that's what this is going down here. But at some point, we start adding positive area to it. And so this curve begins to go upward till it hits 0. When it hits 0, the negative and positive areas are equal. And that is the case here. See if I can show it. Yeah, right there. That's where these two areas are equal. They've added to 0. And now we start going over into more positive area. And the integral, which is this one, begins to increase up until a point. And now we're still positive, but we're adding more negative stuff. And so you see this happening. It's basically similar to the derivative plot that we showed earlier. And if you look at your calculus tables, you can see that is what we expect. All right, let's turn that off. Go back to here. You've got your standard stuff in here. You can invert, change the bandwidth limit, AC or DC coupling. It does not have a built-in terminator, which is fine. You can add your own. Under triggering, you can set up, let's see, where is it? Mode. There we go. Rejecting of high frequency or low frequency. I got into glitch triggering somehow. Edge. There we go. High frequency means radio. Low frequency means audio. So if we reject the audio, we don't trigger, obviously. If we reject RF, then we trigger just fine. That's what you would expect. Another thing I like about this scope is, like all digital scopes, you can pause the display. It's paused now. I can go zoom in and look at it. That's probably the #1 thing I like about a digital scope over an analog scope, is the ability to just freeze the display whenever you want. I know there's storage scopes for analog, but it's not the same thing. Another interesting thing I'll show you real quick, if we go into the Fourier transform, let's see, make sure we get enough data here. Okay, there it is. You see it right here. I pause the display. I zoom in. The Fourier transform gets recalculated from what's being displayed on the screen. If you do things like this, you get some kind of interesting results here, because you've inserted this huge discontinuity. And of course, the Fourier transform assumes a signal is periodic, so it repeats this empty space with the signal over and over again and does its algorithm, and you get some interesting results like this. Those of you who took systems and signals will recognize these waveforms right away. And of course, we can just hit run anytime we want to fix that. We can turn off the waveform display if we want to only see the Fourier transform. Pretty cool stuff. Another interesting topic to look at here is RF. Now I've got the RF generator turned on over here. I'm going to set the frequency to, let's say 20 megahertz. Now we got to zoom in here. We got to trigger it as well. Let's see, edge triggering from A1, mode, turn the rejection off. There we go. Okay. I didn't put a terminator in. Well, I don't know where my terminator is, so leave that alone for now. So here we've got 20 megahertz frequency. Let's measure it real quick. Time, A1, frequency. There it is. Shows 10 megahertz. Oh, isn't that interesting? Well, I did that wrong. Let's see. It is 10 megahertz. That's a 10 megahertz signal. I had this on TX test accidentally, but receiver test is how you make it transmit. So, okay. And we're talking about the Marconi up there. That's what I'm using. All right, so we're at 10 megahertz. RF coming in here, measured as 10 megahertz. RMS voltage is 1.03 volts. Could we take a Fourier transform of this? Absolutely. Let's do that real quick. So in this case, the center is 240 megahertz, and that's not useful. We're looking at a 10 megahertz signal. So we can zoom and change it. There we go. You can see the signal pretty well here. Let's get a cursor on here. So the peak here is at 9.961 megahertz. That's probably actually 10.0, but this is not the most accurate instrument here. And then we've got a harmonic. Look at that, at 20 megahertz. And of course, another one over here at 30. How many dB down is it? I don't know. Let's see if we can find out. It's 10 dB per division. So up here, 1, 2, 3 divisions down. So that's 30 dB down. Now, let's increase the frequency and see if we really get 100 megahertz bandwidth out of this, and I don't think we will. Let's go to 20 megahertz. Scoot it over nicely. And we can look at this, like a normal person would. Let's turn off the Fourier transform. We know what that's going to do. Off. There we go. Okay. Cursors, clear cursors. Okay. 25 megahertz. $50 megahertz. Now this time division knob is telling me it's at the limit. It won't go any further. You see that message down here. Well, let's increase the frequency. Frequency measurement down here. Megahertz. Okay, let's go to 51 megahertz. Okay, 60 megahertz. $80 megahertz. Still measuring, which is good. But you see how it's filling it in like that. 90 megahertz. It's reading correctly down here, 99 megahertz. 100 megahertz. And we've seen only a small reduction in the level, which is interesting. I expected it to be 3 dB down at 100. But it isn't. All right, can we go past 100? How about 102 megahertz? Yep. 150. We don't have all day, right? There's 150 megahertz. And it's even reading correctly. 190 megahertz. Now we've lost some amplitude for sure. If I had the terminator on, this would be a more accurate test because we don't really know the voltage at this end of the cable without the terminator. Well, we know it, but it's not as well determined by the source. Okay. 199 megahertz. It does not like that. But there it is. My understanding is, even though it's not sampling that fast, it varies its sampling a little bit to fill in the gaps and kind of assemble what's actually happening. 200. Here's 200 coming in. And it's showing here 200 megahertz. 210. Wow. So I think for a non-periodic signal, this would be an utter failure, but for something very smooth and periodic like this, it's okay. Let's go to 250. There it is. Only 140 millivolts coming through. I'm sending 500, which is not terminated, so you expect to see about a volt here. 280. Now we're getting pretty noisy. You see this jumping around a little bit. Now I can send it a little more signal, I think. No, I can't. That's the most I can send from this generator. So I would say we're done here. I'll just go ahead and do 300 for fun, but don't expect much. There's 300. I suppose this is where we could turn on averaging and achieve something a little better. Wow, not bad. We don't need that many samples. 8 should do. You turn off the vectors, you see the dots of the individual samples. It's kind of neat. Let's turn it back on though. All right, 320. Oh, now it's done. So now we're seeing an aliasing effect, right? There's a sort of swoop to it you see here. If I go higher, you'll see even more of that as it undersamples the waveform severely. Let's go to 375 megahertz. Yikes. Yeah, there it is. It's entertaining to watch it fail this badly. Frequency not found. Yeah, it's trying. 400. Yeah, it doesn't know what to do here. Turn on averaging, try to smooth it out a little bit. Look at that. It really is trying to do it. I did not expect it to really attempt things beyond, its specification. I'm sure it's not spec to 400 megahertz. 500. Yeah, I don't think we're getting to 500. About 490. Uh, 475 again. $450. I'm just doing this to clear out the average buffer. Well, it's trying. 400. I'm going to say you can measure up to 400 megahertz here, but not very well. But that's still pretty cool, you have to admit. If I hit delayed here, we can't zoom in. That's funny. Okay. So there you have it. Just barely seeing 400 megahertz on a 100 megahertz digital scope. Pretty cool. Lastly, I wanted to show an application of XY mode. And here we're looking at a video a friend of mine made with a binaural microphone. And if we go to display, horizontal, and choose XY mode, we can see the correlation between the left and right microphones pretty clearly. When it's a diagonal line, it's basically a mono signal that comes into both microphones the same. But when it expands, there's a phase difference. When the line tilts, it's just an amplitude difference. And so you can often see some pretty cool patterns like this. I'll link to the video in the description if you guys want to see it. It's pretty cool. There we go. And as you can see, it's quite responsive. Anyway, hope you enjoyed this video, and catch you next time. 7-3.